In this video, we're going to start looking at some basic wave quantities. Last video, we looked at the basic two types waves, the definition of a wave actually was, the transfer of energy through a medium, but the medium doesn't actually go anywhere overall. We looked at transverse wave, we looked at longitudinal waves and stuff like that. So we're going to look at some other quantities, especially the quantities that waves all have in common. Now, one of the ones we had last time that all waves have in common, of course, was the wavelength, and that was the Greek letter lambda. Okay, so all waves have wavelengths. We also looked at something like amplitude, but amplitude usually don't measure that in a longitudinal wave. It's more of a transverse wave type of thing. Transverse waves have the crests and the troughs. Longitudinal waves have the compressions, refractions, but wavelength, that is with all of them. Now, another basic property or quantity that would be really important for waves, since waves are all about moving energy from one place to another, is speed. We often talk about the speed of a wave. Now, the basic way to calculate speed that you guys have, of course, is speed is equal to distance over time, and we often write the average on there. We won't have to worry about average of this because waves just travel at specific speeds. The waves don't accelerate and stuff like that, so just basic dTV is just fine. But what we can do is we can specialize this a little bit. What we can do is we can specialize this. We can look at this distance right here. Instead of just using any random distance, we can actually do the distance for one wave. And the distance for one wave, that is the wavelength. But if we're using the distance for one wave, we have to use the time for one wave. Now, the time for one wave is what's called the period. And the symbol for period is the time for one thing to occur. And the symbol for that is a capital T. And this is why when you guys are doing basic kinematics and all that kind of stuff, when you're writing time, you can't put a capital T because a capital T is a very specific kind of time. It stands for period. So if we use the distance for one wave, which is the wavelength, we can use the time for one wave, and that's called the period. So we can rewrite this as wavelength divided by the period. Okay, now periods actually, you guys have been using that term like for years, not even realizing it. There's a reason why your class is called a period, because it is a set amount of time that happens over and over and over again. That's why it's called a period. So first period, second period, third period, whatever it is. Okay, now related to period is another really common quantity that you guys have heard of, and that would be the frequency. Now, how frequently a wave occurs is a really common quantity. And frequency is defined as how many waves in a given amount of time. Okay, so frequency is how many waves there are divided by time. Now, this is directly connected to period, because period is the time for waves, and frequency is the waves per time. These two are actually inverses of each other. So frequency is actually the inverse of period. One is the waves per time, the other one is time per waves. So they're actually inverses of each other. So if we go back to the expression over here, we have speed is wavelength divided by period. But dividing by period would be the exact same thing as multiplying by frequency, because frequency and period are inverses of each other. Okay, so we've got a couple other quantities we're kicking around here, so let's sort of lay these out a little bit. We have what's called the period, and this is the time for one wave to occur. And then if we invert that, that is where we got our frequency from. And this is how many waves. It's not really per time per se, it's actually per second. So period is seconds per wave, and frequency is waves per second. So these two are inverses of each other. These guys right here, those guys are inverses of each other. Okay, so these are four basic quantities that all waves have, no matter if they're transverse, longitudinal, it makes absolutely no difference. They have them all in common. Now, what we end up with over here at the very end is V is frequency times a wavelength. This is called the wave equation. And it does not matter what kind of wave you are talking about, this equation applies to any kind of wave, and that's why it's called the wave equation. And it is probably the #1 formula and expression used for all types of waves, no doubt about it. Okay, and we will use it a lot. Okay, so let's start practicing with some of these ideas and see what we can do. Okay, so let's try this. Suppose we have some, some water waves, you're saying it's some water, something like that. Here we've got, like a rock or something like that. And here's just a person just chilling on the rock. This. Watching the waves go by. Okay, so let's see what we can do here. And let's sort of get this laid out a little bit nicer. There we go. There we go. That's a little bit. Just trying to get the top of the waves a little bit more obvious there. There we go. That's a little better. Okay. Okay, there we go. So let's say we got some waves here. And let's say the distance from here to there, that's going to be 6.2 meter distance. And let's say the waves go by, he's watching the waves go by, and the waves are 1.3 hertz waves. And if you're not familiar, hertz is the unit for frequency. Frequency, like, radio frequencies, any kind of frequency you want, they're measured in hertz. Okay, so let's find out the speed of the waves. Okay, well, that's no problem. Speed is frequency times wavelength, so we can figure that out. We've got the frequency, we just got to get the wavelength. So if I look at the waves, I got that 6.2 meters, but that's not the wavelength. That is for a bunch of waves. If I look at it, I've got one wave starting here. It goes through one complete cycle. There's one wave, there's two waves, there's three waves, and there's four waves. So I've actually got four waves. So to find the wavelength, I actually need to take that 6.2 and divide it by 4 in order to get the length of one single wave. So if I do that, the wavelength would be about 1.55 meters. All right. So now that I have that, I've got my frequency, I've got my wavelength. I will just multiply those two together, and my waves are going around 2 meters per second. All right. Okay, so let's try something else. All right. Suppose we take some light waves. Okay, so here we're gonna. There's the sun, and we've got some light waves. All right, and let's say the waves are going by, and I don't know why you'd be watching them, but whatever, it doesn't make any difference. But let's say 8.64 times 10 to the 17 waves actually go by in, let's say, 30 minutes. Okay, and I want to know what is the wavelength of those of that light right there. Okay, well, let's see if we can figure this out. I'm looking for the wavelength. Well, how do I find wavelength? Well, wavelength is going to be the speed divided by the frequency. Well, speed, I mean, these are light waves. Well, the speed of light is the speed of light. So that's the symbol c that we've used before in fields, and it's also in your super sheet. So we also just need the frequency. So to find the frequency, that's how many waves per second. So I've got 8.64 times 10 to the 17 waves divided by how many seconds there are. But that's in 30 minutes. I don't want the minutes. Of course, I want that in seconds. So if I convert that, that would be 1800 seconds. So I'll divide that by 1800. All right. So if I do the 8.64 to the 17 waves, that's how many waves I've got. Divide that by 18 seconds. I've got 4.8 times 10 to the 14 hertz. And that's how many waves per second I've got. Okay, so I can take that and I can put that into my other expression. So I found my frequency that goes there. The v would just be the speed of light in a vacuum, because we're about vacuum type stuff, and I can then calculate the wavelength, and of course wavelength for lights can be really small. And if we calculate it, we get about 6.25 times 10 to the negative 7 meters, or 625 nanometers, which is a really common way to talk about light. Okay, So 625 nanometers, that is actually in the visible spectrum. You could see that. That probably like an orangey reddish type color. So maybe more of an orangey reddish type color, probably more reddish than anything else. And that's what that would be. Okay. All right. Well, let's get rid of this and try a couple other questions. All right. So, let's say you've got a great big speaker giving off sound waves. Okay, listening to some music, and there's a guy over here just dancing to the music. And let's say he's 23.5 meters away from the speaker, and let's say this thing is giving off 125 hertz sound wave. Okay, now we're talking about sound waves, so we can work with that a little bit. He would probably hear the sound. It would probably about 0.07 seconds. So it takes 0.07 seconds for waves to actually reach the little dancing guy. So what is the wavelength coming out of here? Okay, so we're going to try and find the wavelength. Okay, well, a couple things we can do here. First of all, one of the things that pops out to me is I've got distance and I've got time. And with distance and time, I can find speed. So speed would be distance divided by time. I've got the 23.5, I've got the 0.07, and that means I get about 336 meters per second. And sound travels around 340, so that's about right. So sound travels around 340, we got 336 for speed, so that's all taken care of. And then to find the wavelength is V divided by frequency. Well, I've got my V right there. I've got my frequency right there. So I just have to divide them out, and I get a wavelength of around 2.7 meters. So almost 3 meters long. So this would be a really, really low type, crazy subwoofer type wave. Maybe almost 3 meters long. Okay, all right, let's try something else. Suppose we've got some grass, and we got over there. Let's draw a little. Here we got some little brother and a sister here playing with a rope or something like that. I'll give him some hair too. There we go. All right. So suppose they've got a rope between them, and draw something like that. There we go. And they're just wiggling a rope back and forth. And let's say they are 9 meters apart. Okay. Let's say they shake the rope at 0.85 hertz. Okay, so I want to know how fast are the waves moving on the rope. Okay, so looking for speed again. So speed is frequency times wavelength. Okay, well I have the frequency, that's easy, that's no problem, but I need to know the wavelength. That's not 9 meters. Okay, if I start here, this would be one wave, that's one complete cycle, and then I've got half a wave. So that's actually 1.5 waves. So if I divide the 9 by 1.5, I can see that my wavelength is actually 6 meters. Okay, so I've got a 6 meter wavelength in there. Okay, so here's my frequency. I had that to begin with, and I've got my 6 for my wavelength. So I'll multiply my 0.85 times my 6, and I got a V of around just over 5 meters per second. So that's how fast the waves are going on the rope. Okay, so this is just some general practice using the quantities. Period hat didn't really come up, but that's just the inverse of frequency. And generally straightforward calculations, no big deal. But we'll be using these expressions quite a bit, and these are just some examples of the applications of using them.